Welcome to today's deep dive. I'm so glad you're joining us. Whether you're prepping for a high-stakes software architecture meeting this afternoon, or, you're just intensely curious about the hidden mechanics of how coding actually works under the hood, you are in the exact right place. We've got plenty of aha moments lined up for you today.
We really do. And we're taking a look at a fascinating piece of source material. It's an excerpt from a tech-reader.blog article by tech writer Aaron Rose.
Right.
And the title alone gives you a hint of what we're dealing with here. It's called The Secret Life of Python, the Pickle Jar.
The pickle jar. I love that. Our mission for this deep dive is to completely demystify this weirdly named Python concept called pickling.
Yeah, it's a pretty great name.
It is. And we're going to figure out exactly why we hit a massive brick wall when we try to copy certain objects in our code. Plus, we're going to uncover a severe security warning that's just kind of hiding in plain sight when you use this tool.
Exactly. It's one of those topics where the surface level seems like, simple data storage. But once you start digging into the actual architecture, you realize how deeply it ties into the core of how programming languages interact with the operating system's kernel.
So to set the scene, our source introduces us to this incredibly relatable scenario. We have a programmer named Timothy, and, well, he's having a rough day.
We've all been there.
Right. He's trying to do something that seems conceptually straightforward. He just wants to copy a live database connection within his Python application. But instead of a clean duplication, he's met with this really cryptic type error.
And the error specifically mentions something called a thread lock.
A thread lock, which is weird, right?
Seeing an internal threading lock surface in an error message when you just want to duplicate a database connection, yeah, that is usually a sign that you're fundamentally misunderstanding how the language manages memory.
So Timothy's mentor, Margaret, steps in. She looks at his screen and explains why Python is essentially throwing its hands up and saying it cannot pickle the object.
Margaret explains to Timothy that pickling is just Python's terminology for a standard yet highly complex programming concept: serialization.
Serialization. Okay,
Right.
Let's unpack this. What is actually happening at the bytecode level when we serialize or pickle an object?
Well, think about a complex Python object.
Mhm.
Margaret uses a basic example of a dictionary containing a string and an integer.
Just a simple key-value pair.
Right. But in a real-world architecture, we're usually talking about massive object graphs. When that object is alive inside your running program, it's this multidimensional structure living in your computer's RAM.
It has pointers, memory addresses.
References to other objects, exactly. But when you need to save that state to a disk, send it over a network, or perform a deep copy across different processes, you run into a physical limitation.
Because you can't just shove a living, non-contiguous block of RAM memory addresses through a network cable.
No, you can't. The receiving machine wouldn't know what to do with those arbitrary pointer addresses. They mean absolutely nothing outside that specific process.
So you have to translate it. Python has to take that complex living object graph and flatten it out into a linear series of ones and zeros.
Margaret calls this translating the object into a byte stream.
I love the visual Margaret draws on the whiteboard in the source. She literally draws an arrow from the Python object to this long, messy line of hex digits.
Oh, the hex dump.
Yeah, it looks like \x80, \x04, \x95, and so on. I mean, to a human, it's absolute gibberish.
But to the Pickle module, that gibberish is actually a highly precise set of opcodes. This is where we move past the basic idea of just translating data.
Because it's not just, making a CSV file.
Right. Pickling doesn't just convert data into a text format. The Pickle module essentially operates its own internal engine. It's called the Pickle Virtual Machine, or PVM.
Wait, a virtual machine entirely dedicated to reassembling data?
Yeah, it's a stack-based virtual machine. When you see those hex digits, you're actually looking at a program written in a bytecode language specifically designed for the PVM. The \x80 opcode tells the machine which protocol version is being used. Then the subsequent opcodes instruct the PVM to push items onto a stack, pop them off, build dictionaries, and even instantiate custom classes.
So the PVM is acting as a master blueprint maker. It traverses your complex object graph and systematically records the specific instructions needed to rebuild it from scratch.
It writes down the type of the object, the attributes it has, and the raw data. And the PVM also utilizes a critical secondary data structure called a memo.
A memo. Like a scratch pad.
Basically, it's an array that keeps track of every object the PVM has already serialized during the current session.
Why does it need a memo, though? If it's just writing a blueprint, shouldn't it just serialize everything it touches?
Imagine you have a directed cyclic graph. Object A has an attribute pointing to object B,
Okay.
and object B has an attribute pointing right back to object A.
Oh, I see.
If the PVM blindly followed pointers, it would bounce between A and B forever. It'd be an infinite loop.
So the memo prevents this. When it encounters object B's reference back to object A, the PVM checks its memo.
It realizes it's already serialized object A and simply writes an opcode that says, insert a reference to memo item number 1 here.
That is brilliant. It prevents the loop and keeps the byte stream incredibly efficient.
And then comes the reverse process. Margaret calls it unpickling,
which is where Python feeds that byte stream into the PVM. The virtual machine reads those specific opcodes, uses its stack and memo, and constructs a brand new identical object graph right there in the computer's memory.
It constructs a new environment that behaves exactly like the original one did at the moment it was pickled. It's a highly capable system for capturing the entire state of an application's data.
But wait, if it's a fully fledged virtual machine capable of handling complex graphs, why did Timothy's code crash? He was just trying to copy his database connection. And here's where it gets really interesting.
It does. If we connect this to the bigger picture, we have to look at what Margaret draws next on the whiteboard.
A brick wall.
She draws a literal, solid brick wall. On one side, she writes user space memory.
And on the other side, she writes operating system kernel.
The OS boundary. This is the brick wall that Timothy smashed his code right into.
Because the Pickle module's virtual machine is incredibly smart, but its jurisdiction is strictly limited to Python's user space memory.
Right. It can only record data and state that lives entirely within the memory allocated to the Python process.
And a live database connection is not fundamentally a Python object.
No, a database connection relies on a file descriptor. At the kernel level, a file descriptor is just an integer index.
It points to an entry in the kernel's process control block,
which in turn points to a complex structure that represents an open network socket.
So Python goes to the operating system and requests a network connection to the database. The OS kernel handles the heavy lifting, allocates the resources, and hands Python back an integer, say socket number 42.
Python's database connection object just acts as a wrapper around that number 42.
And that file descriptor, number 42, is transient. It only has meaning to the kernel for that specific process at that specific moment in time.
While the network connection is actively maintained.
So if the Pickle virtual machine tried to serialize that database connection, it would just write down an opcode that says, to rebuild this object, use socket number 42.
And if you saved that byte stream to a disk and tried to unpickle it an hour later, or on a completely different server, Python would faithfully rebuild the wrapper object.
And it would try to send data down socket number 42.
But the kernel context is gone. The operating system might have closed that socket. Or, even more disastrously, the OS might have recycled socket number 42 and assigned it to a completely different application.
Your database query might accidentally be sent to a local printer service.
Or an external web API.
That would be an absolute nightmare to debug.
Because a connection crosses the boundary between Python's controlled memory space and the dynamic environment of the OS kernel, the Pickle module refuses to make assumptions.
Rather than handing you a corrupted object that causes silent failures, Pickle throws a type error. It hits the brick wall and stops.
You cannot pickle objects tied to kernel-level resources. Network sockets, open file handles, memory-mapped files.
And as Timothy saw, thread locks. But why are thread locks included in that list?
Because a thread lock in Python is ultimately backed by an operating system primitive. Usually a futex.
A fast user space mutex.
Exactly. The kernel manages the queue of threads waiting for that lock. Python can't serialize the kernel's internal queue.
Oh, that makes sense.
I've actually seen experienced developers spend 3 straight days debugging a massive application crash caused by a type error identical to Timothy's.
Really? 3 days?
Yeah. They were trying to pickle a huge custom configuration object. Buried 5 layers deep in that object's dictionary was a custom logging handler.
Let me guess. That logging handler had initialized its own internal thread lock.
To prevent concurrent file writes, yes.
The entire serialization process failed because of one hidden lock deep in the object graph.
The PVM traversed the graph, hit the futex wrapper, and immediately threw the type error. When Python says it cannot pickle something, it's telling you that you're trying to smuggle a kernel-managed resource across the boundary in a plain text envelope.
It simply won't survive the trip.
Margaret doesn't just leave Timothy with architectural theory, though. She shows him how to interact with this process using practical code snippets. She writes out a cheat sheet for him.
Right, she starts with a standard, self-contained piece of Python data. A small dictionary. Data equals open brace, matches :10, active :true, close brace.
And she uses the command pickle.dumps. Dumps with an S standing for dump string. Passing the data into that function invokes the PVM, which spits out the raw hex-digit byte stream.
And to reconstruct the memory state, you use pickle.loads or load string.
That handles the automatic traversal. But Margaret introduces an advanced architectural feature for situations where the automatic PVM behavior just isn't enough.
Like what?
Well, if you have a custom, highly complex class that manages its own internal state, you can actually take manual control of the opcodes.
Like something that normally holds a file descriptor, but you want to tell Python how to safely disconnect and reconnect it during serialization. How do you manually dictate what the virtual machine writes down?
You define a dunder method on your class called dunder reduce.
Dunder reduce. By implementing that, you bypass the PVM's default blueprinting. You are explicitly telling the pickler, do not guess how to dismantle me. Use these exact instructions.
Precisely.
So what does dunder reduce actually look like? What is it giving to the PVM?
The method must return a tuple. The most critical parts of this tuple are the first two elements: a callable object, usually a class or a function, and a tuple of arguments to pass to that callable.
Okay.
When the PVM is writing the byte stream, it records the reference to the callable, records the arguments, and then writes a specific opcode called redo-te.
So when the byte stream is being unpickled later, the PVM hits that redo-tc opcode.
It pops the arguments off the stack, it pops the callable off the stack, and then it executes the callable with those arguments to reconstruct the object.
It gives you ultimate arbitrary control over the reconstruction phase. That level of manual control is incredible for custom architecture. But it leads to a question Timothy asks. Is Pickle the only serialization tool we use? If I need to save data or send it across a network, do I always reach for the pickle jar?
Margaret's answer is a resounding no. Pickle's ability to maintain complex object graphs and retain Python-specific class structures makes it incredibly powerful. But that power limits its interoperability.
It is strictly a Python-to-Python technology. It speaks a bytecode language that only the Pickle virtual machine understands.
If you take a Pickle byte stream and send it to a front-end interface built in JavaScript or a microservice written in Go, those environments will look at the hex data and fail. They don't have a PVM.
They don't have a pickle.loads function.
So if you're building cross-language APIs, you have to pivot. You switch to JSON. Margaret describes JSON as the universal language for data interchange. It's a standardized text-based format. Go, Rust, JavaScript, and Python can all parse and generate JSON natively.
It serves as the perfect bridge between disparate system architectures. But Margaret also points out a severe limitation with JSON compared to Pickle.
JSON represents a strict hierarchical tree. Because it has to be parsable by every language, it caters to the lowest common denominator of data structures.
It only handles primitive types: strings, numbers, booleans, arrays, and standard key-value maps. JSON can't handle complex, custom Python classes.
It strips away all the behavior and internal state. Furthermore, JSON cannot represent directed cyclic graphs. If you have an object that references itself, a JSON parser will typically hit maximum recursion depth and crash.
So JSON is purely for tree-structured data transfer. If you're sending a list of product IDs to a web browser, JSON is the industry standard.
But if you need to pause a complex machine learning model with millions of interconnected nodes, save its exact memory state to disk, and resume training it on a different compute cluster tomorrow,
you need the full graph-traversing power of the Pickle virtual machine.
that distinction dictates your architecture. Pickle is for deep internal state preservation. JSON is the universal translator for external communication.
However, Margaret introduces one final non-negotiable rule about pickling. And the source explicitly notes a sharp change in her tone here. The conversation becomes significantly more serious.
This raises an important question about trust and security. Margaret establishes the golden rule of serialization. You must never, under any circumstances, unpickle data from a source you don't trust.
Never unpickle untrusted data. We understand the PVM is just following the blueprint, but how dangerous can it actually be to read instructions?
Let's look closely at how the dunder reduce method operates. We established that reduce returns a callable and a tuple of arguments.
Right, and the PVM executes that callable during the unpickling process. It pops them off the stack and runs them.
What happens if a malicious actor crafts a custom byte stream? They don't have to send you a serialized dictionary. They can send you a byte stream containing a customized reduce opcode.
Okay.
They format the byte stream so that the callable pushed onto the stack is Python's built-in os.system function.
Wait, the function used to run terminal commands on the operating system.
Yes. And they format the arguments pushed onto the stack to be a string like arm-arf/, or a script that opens a reverse shell to a remote server.
Oh my gosh. Because the PVM doesn't know it's supposed to be building a data model. It's just a virtual machine executing opcodes.
The moment your application calls Pickle loads on that malicious byte stream, the PVM hits the RDCE opcode. It pops the malicious arguments, pops os.system, and executes it.
It runs the shell command before the loads function even finishes.
The damage is dealt instantly. It is arbitrary remote code execution masquerading as data deserialization.
Your application, running with whatever kernel privileges it holds, just handed the operating system a command to wipe the disk or open a backdoor.
That is a staggering vulnerability.
It's remote code execution happening entirely in the background, simply because you tried to load a file.
Because the PVM is designed to rebuild complex logic, it can be seamlessly weaponized to execute malicious logic. It demands a completely secure, zero-trust environment.
So how do you apply this to your own architectural decisions? Margaret's cheat sheet is clear. You only ever use pickle.loads on data that your own system generated, or data received over an encrypted channel from a strictly verified internal microservice.
If you're downloading a serialized machine learning dataset or a pre-trained AI model from a public repository, you are taking an immense risk if you run pickle.loads on your local machine. You are effectively handing your terminal to a stranger.
When dealing with untrusted data payloads from the outside world, you use JSON. A malicious actor cannot execute an OS-level command through a basic JSON string because a JSON parser doesn't utilize an execution engine, it just reads text.
Exactly.
So what does this all mean? We've covered some intense architectural ground today based on Aaron Rose's article.
We really have.
For you, the listener, the takeaways directly impact how you design systems. You can now look at a type error complaining about a thread lock and confidently diagnose the problem.
Python is stopping you from smuggling a transient kernel file descriptor across the OS boundary.
You understand that serialization isn't just translation, it's the Pickle virtual machine executing a stack-based blueprint. You know to rely on Pickle for complex internal graph storage and to pivot to JSON for cross-language API communication.
More importantly, you understand the mechanics of how to protect your server infrastructure. My core belief is that knowing the syntax of a tool is never enough. Understanding how the PVM utilizes the reduce opcode to execute callables is the only way you can truly grasp why deserializing untrusted data leads directly to remote code execution.
Seeing the byte stream as a set of executable instructions rather than passive data makes the security risks logical and obvious.
The underlying mechanics always dictate the boundaries of the tool.
That leads us to a final thought for you to mull over as you analyze your own code bases today. We just learned that an incredibly convenient standard library feature holds the power to execute arbitrary terminal commands simply by loading a file.
Right.
So ask yourself, what other helpful built-in features in Python or any other daily programming language you use are secretly operating as Trojan horses if you don't fully understand their internal architecture?
It's an essential question for anyone designing secure software.
Thank you so much for exploring the secret life of the pickle jar with us today. Keep questioning how the machine works under the hood, and we'll see you on the next deep dive.